So welcome to the second paper session of this year's SummerSOC. My name is Holger Schwarz from the University of Stuttgart, and our first presenter is also from the University of Stuttgart, from the group of Marco Aiello, Ebaa Alnazer. She will talk about the conceptual framework for understanding real-world AI planning domains. So the stage is yours.
Okay, thanks for the introduction. I will present my paper entitled Understanding Real-World AI Planning Domains, a Conceptual Framework. And the paper is authored by me and by my colleague Ilche Georgievski from also the University of Stuttgart. Since the paper is about AI planning, I will start with a small introduction about AI planning for those who are not familiar with the concept. And I will also talk why we need to understand real world and what does it mean to understand real world planning. Okay, so AI planning from its name is a subfield of artificial intelligence. And the focus of this field is to research and develop planning systems. And the idea of the planning system is to compute plans, and the plans are a course of actions that should be executed in order to satisfy some predefined goal. There are multiple techniques of AI planning. They differ in the assumptions that they make about the environment where the planning is taking place, or what we call the planning domain. And those techniques, the most restrictive one is classical planning, which makes really restrictive assumptions about the domain where planning is taking place. And there are some other techniques that do relax some of those assumptions. For example, probabilistic planning, temporal planning, and so on. AI planning has a lot of application domains where it can be applied, starting from games to autonomous vehicles, to rovers, to robotics applications, to also spaceships, and so on. And AI planning is a knowledge-based technique, and by knowledge-based we mean that in order for the AI planning system to compute this plan, it needs an adequate and relevant information given to the planning system that describes the domain where the planning is taking place. And this knowledge is formulated in terms of a planning domain model. And this is where we describe what actions we can perform in the domain, what tasks we can perform, how we can achieve some tasks, and so on. And the problem instance, which is the planning problem that we try to solve in this planning domain. And here where we describe the goal that we want to achieve. Now, the focus of this paper on this planning domain model. And in particular, what we are interested in is how we can define this planning domain model. And in order for the AI planning system to be applicable in real-world settings, it's necessary that this planning domain model really reflects the aspects that characterizes the planning domain where planning is taking place, or the planning environment. So in order for the planning domain model to reflect those characteristics, we have first to understand what characteristics make this planning domain real, and then reflect those on the domain model. Because the reason for this, if we don't understand what makes planning domains realistic, we might end up with a domain model that doesn't really reflect the reality. And this will lead to plans that, when are executed, they don't lead us to the goals that we want to achieve. And if we look at the software development lifecycle of AI planning system suggested by Ilche Georgievski, we see that in the third phase, this is the phase when we develop the domain model. We see that in this phase, it's necessary to understand the realistic aspects of the planning domain, but that doesn't stop here. Understanding the realistic aspects affect all the phases of this development lifecycle. So if you look, for example, at the second phase, where we choose what planning type we want to use, for example, classical, probabilistic, or temporal planning type, we see that we need to understand what aspects or what characteristics in the planning domain exist in order to make the right choice here. This also applies, for example, in the fourth phase where we apply some software engineering concepts. And in order to design our system, we need also to understand the aspects and the characteristics of our planning domain. So this means that understanding the aspects of planning domains should come before all these phases as a first step. Now, the current process that is happening in the AI planning in general is that in order to move from some planning domain that we have in the third phase into a specific domain model that we formulate this planning knowledge or that we have, this process is done as an ad hoc process, which means that there is no support for planning engineers that work in the third phase, and no support for software engineers that work in the fourth phase in this process. So the engineers are not supported in understanding and reflecting the realistic aspects of planning domains in all those phases. And this is where our work comes into play. So the problem statement is that there is no current support for software engineers and knowledge engineers in the process of identifying relevant and realistic aspects of real domains for the development of essential planning elements, which are the phases that we saw before. And the research question that we are trying to answer is that what are the realistic aspects that should be taken into account in the development of the AI planning systems, and how we can organize those aspects. And this brings me to our contribution. The main contribution of the paper is to develop a conceptual framework of those realistic aspects for planning domain knowledge. We call this conceptual framework Realistic Aspects Framework. Now, the intent of this framework is to give guidelines for planning and software engineers in the process of the development of AI planning system. And it gives a common and inclusive notion of what it means for a planning domain to be realistic, to reflect the reality. And this will drive the development of AI planning techniques and services and tools. And this may improve the applicability of AI planning system, because if we understand what makes a planning domain realistic and we can reflect this in the development of AI planning system, we might end up with an AI planning system that can be applicable in real settings. And this provides means for comparing different AI planning systems based on what characteristics each AI planning system supports. Now, the approach that we followed in order to develop this conceptual framework is a four-step approach. And we started with doing a top-down exploratory research on existing literature in order to identify characteristics discussed by existing literature in AI planning. And we wanted to study works that don't only study a specific domain, but we wanted the conceptual framework to be as generic as possible. So we studied also works that talk about quality of planning domains or about requirements of planning domains in general. And from those categories, we identified around 20 studies. And then from those identified studies, we extracted the characteristics that they talk about. Of course, they didn't talk about the characteristics explicitly as we understand it, but they talk about the requirements for modeling those planning domains. Then we end up with some characteristics set, and we took this characteristics set and we categorized the characteristics based on their relevance into categories and subcategories. And we identified 7 main categories in those studies. And then we took those 7 main categories and we generalized and refined them into a hierarchy of aspects or categories. And this is what constructed our realistic aspects framework. And we also defined the relationships between the different categories and subcategories in this hierarchy. So this is how the realistic aspects framework, this is an abstract overview of it. So here we have the 7 main categories that we identified in step 3. And then we have the categories and subcategories here. And we also define the relationships between the different categories and subcategories. Now, in the next slides, I won't have time to explain all those dimensions, but I will point out some of the aspects that are really simplified in the existing literature, or some of them are even neglected in the existing literature. Okay, so starting from objectives, so the objective aspect is related to what is the goal of the AI planning system. And we categorize the objectives based on their types into preferences, which are the non-mandatory behavior of the planning system, and into requests, which is the mandatory behavior, which is why the AI planning system should solve the planning problem. And those can be represented either or expressed either qualitatively or quantitatively. And we also defined different granularity for the goals. So the goal can be an abstract of other goals, an abstraction of other goals, or it can be a sub-goal of the goals. Now, the second high-level aspects are related to tasks. And we categorize tasks based on their complexity into actions and complex tasks. And by actions, we mean these are the tasks that can be performed directly. For example, turning on and off the lights can be considered as an action. Or a complex task, which are tasks that cannot be executed directly, but they provide a rich knowledge to the AI planning system. So, for example, keeping the light level at a comfortable level in the room could be considered a complex task, and this can be achieved by executing different actions. And from this categorization, we can also define relations between those tasks, and those relations can be abstraction levels, which means that the complex tasks represent abstraction levels of the actions that are used to perform those complex tasks. And also there can be alternatives. So for example, if we have complex tasks, there can be multiple ways to execute this or to perform this task. Okay, we also defined other relations, but I won't go into details into them for now. Okay, the second dimension is about determinism. And determinism means that, so if we have a deterministic domain, it means that this domain, all the environment conditions in the domain are known during the planning, and we know all the consequences of our actions. So for example, if we have a smart building and we have a cleaning robot in the smart building, so if the robot wants to move between rooms, for example, we know with certainty that the robot will move eventually to the destination. And we also know, for example, the time taken by the robot to move between these rooms. However, most of the domains, the planning domains, are non-deterministic, which means that we cannot know for sure that the consequences of our actions. And we don't have a fully observable environment around us. So if we have a cleaning robot again, there can be some fault in one of the sensors of the robot, so the robot cannot observe its full environment. And the non-determinism comes from the uncertainty in the environment. So if we are talking again about the cleaning robot, the people that are moving while the robot is cleaning can be considered some source of uncertainty that will affect the actions of this robot. And we distinguish between what is called risk and what is called uncertainty in the consequences of the actions of the robot. And the risk is a situation where we know some probability information about the probability distribution of the outcomes of the actions, while uncertainty is a situation where we don't know the probability distribution of the actions, or we have partial knowledge about this probability distribution. And this is where most of my research focuses on. Now, when we have this non-deterministic environment, this affects the behavior of the agents in this environment. So, and if we have these risky situations or uncertain situations, agents that are performing actions in the environment can have different behaviors risk tolerance. So agents can be, for example, risk-seeking. So if they are confronted with multiple choices, they tend to go for risky choices, and they are called, in this case, risk-seeking. Or they can avoid risky choices and go for more guaranteed ones, and they are called risk-averse in this case. There are also risk-neutral agents who don't care about the risk, and they take the average. They try to maximize the average of the outcomes of the different choices. We also distinguish agents based on their types into components and human agents. So components are all the entities except for human agents. Those can be robots, devices, software components, and so on. The last dimension that I want to talk about, or the last high-level aspect that I want to talk about, is quantities. And quantities is anything that can be measurable in the planning domain. And we distinguish quantities based on their type into resources, action costs, and environmental inputs. And resources give some limitation to the highest consumption that we can consume in the planning domain. So if we're talking again about smart buildings, one of the resources could be the energy that is stored locally. We cannot consume more than what we store locally. Action costs are the same that we, in the cleaning robot, action cost could be the time that is needed by the robot to move between the rooms. And environmental inputs are things like the CO2 level, the humidity, the temperature in the environment, and so on. Of course, the way to compute the quantity depends on what this quantity represents. So if we have, for example, the temperature, we need nonlinear function in order to compute it. Okay, so I won't go into detail about the remaining two aspects, the constraints and the qualities, but I want just to mention that those aspects are not only related to the planning domain itself, but they also have characteristics that characterize the AI planning system in general. So we can define also qualities for the AI planning system, including how modular it is, how maintainable it is, and so on. Okay, so this brings me to my conclusion. So we saw that the applicability of AI planning system, it seems that it's still a challenging task. And one reason of this could be that there is a broad range of aspects that characterize real-world planning domains, and those aspects are really not understood. So there is no definition of what makes a planning domain realistic. And we need support for knowledge and software engineers in the process of developing AI planning systems. And this made us create a conceptual framework that conceptualizes the notion of planning domain realism and drives the development of service-oriented AI planning systems, and offers means for comparing the different AI planning systems. And most importantly, we highlighted some aspects that are either simplified in the current literature in AI planning or neglected. Now, for future work, we want to synthesize metrics that can quantitatively measure the realism of AI planning systems. And we want to empirically verify and validate the conceptual framework on realistic planning domains. And lastly, we want to explore the usability of the framework for the design of service-oriented AI planning systems. Thanks for listening. That's all from my side.
Okay, that's the work. Thank you, Ebaa, for your presentation. So the basic idea of the paper sessions was to move all the questions to the poster session at the end of the week. But anyway, while the next speaker set up, if there is a very urgent question, we can do it just now. And if not, you can ask Ebaa in the poster session, as I said. Okay, so the next presentation is from the University of Groningen, and Mustafa will tell us about empowering machine learning development with service-oriented computing principles. And as soon as we have the right picture, you can start. a nice picture. I wouldn't dare to eat them.